Hi Chem 30s. So we're going to look here at lesson 1 part 2, which I am just kind of considering from standard cells and cell potentials onwards, just because I feel that the video I shared from you with that guy Tyler DeWitt does a really good job explaining some of the previous parts of lesson 1. So we're going to keep going here with lesson 1 part 2. And a standard cell is a voltaic cell in which each half cell contains all entities shown in the half reaction equation at SATP conditions with a concentration of 1.0 moles per liter for aqueous solutions. All right, so we have to be working with our solutions as an aqueous solution. And what you'll notice is that everything has to have a concentration of 1.0 moles per liter for this to happen at SATP conditions. So the standard cell potential, which is E naught cell, is this voltage produced by the cell operating under standard conditions. The standard cell potential represents the energy difference between the cathode and the anode. So we got to go from the cathode to the anode. Okay. The degree sign indicates that standard 1.0 moles per liter and SATP conditions apply. A standard reduction potential, which is E naught R, represents the ability of a standard half cell to attract electrons, thus undergoing a reduction. The half cell with the greater attraction for electrons, that is the one with the more positive reduction potential, E naught R minus, gains electrons from the half cell with the lower reduction potential. The standard cell potential, give this a highlight, the standard cell potential is the difference between the reduction potentials of the two standard half cells. All right. So this is our voltage. This is our strongest oxidizing agent. And this is our strongest reducing agent. So remember that our SOA is up here, and they get weaker as they go down. And our strongest reducing agent's down here, and they get stronger as we go up. And it looks something like that. All right. Tells us to draw the cell below and label all the necessary parts. So you would have had a little bit of practice of that. I'm going to leave that for now because I want to get onto the next section here, which is talking about this standard hydrogen half cell. It is impossible to determine experimentally the reduction potential of a single half cell because electron transfer requires both an oxidizing agent and a reducing agent. To assign values for standard reduction potentials, we measure the reducing strength of all possible half cells relative to an accepted standard half cell. All right, so it's kind of like saying you have point A, B, and C. And you don't know the difference between any of these, but maybe you'll call this 100, maybe you'll call C 50, and maybe you'll call A 200. If you don't know what these values are, you don't know how to space them out. So if we did something like that, this would have to be a little bit further up. Like so. All right. The half cell used for this purpose is the standard hydrogen half cell. What you'll see is that if you look in your data book and you go to that reduction table, what you'll see is your E naught value. So it looks like this is equal to 0.00 volts. A half cell that is chosen as a reference and arbitrarily assigned a reduction potential of exactly 0 volts is called a reference half cell. So we can refer to it in regards to what oxidizes and what reduces. The standard hydrogen half cell consists of an inert platinum electrode immersed in a 1.00 mole per liter solution of hydrogen ions and hydrogen gas at a pressure of 100 kPa, kilopascals, bubbling over the electrode. So this reaction can happen with a few different things. So we have here our voltage of 0.34, and we have here a voltage of 1.66 volts. When you look inside your books, at that reduction table, you will see that this half reaction here, its electrical potential is plus 0.34, and the electrical potential of this half reaction is negative 1.66. Because we have assigned the hydrogen half cell a reduction potential E naught R of 0, we can now assign values to the other half cells by connecting them to the hydrogen half cell and calculating the cell potential. A reduction potential that has a positive value means that the oxidizing agent is a stronger oxidizing agent than hydrogen ions. A reduction potential that has a negative value means that the oxidizing agent is a weaker oxidizing agent than hydrogen ions. We can measure the standard reduction potential of a half cell by constructing a standard cell using a hydrogen reference half cell and the half cell whose reduction potential you want to measure. So we have our cell set up here. This is a copper hydrogen standard cell. So what we see here is we have that H2 gas at 100 kilopascals. We have our platinum electrode. Then we have our copper electrode. And we have our copper 2 plus solution at 1.00 moles per liter at 25 degrees Celsius. Now, what we have to do is we have to determine what's happening at our anode and what's happening at our cathode. So usually when we draw this, we like to do our cathode on the right, anode on the left, and we're going to say that, when we draw it like this, that way we know that our electrons flow from anode to cathode. Make that a little clearer there. So electrons flow from anode to cathode. So at our anode, the reaction occurring there, we're going to do this a little backwards, is that hydrogen gas. And we can just use that reduction reaction in our data books, which is H2 gas. Oops, sorry, this is an oxidation. The anode, we have oxidation. And at the cathode, we have reduction. So at our anode, we have H2 gas, which becomes H plus ions. And at our cathode, we have copper 2 plus ions, which becomes copper salt. So what's happening is that this, if we were to measure this mass here, and we found out it was 450 grams, and we let this cell continue for a bit, and we pull it out again, we might find out that our mass now is 454 grams. So it's actually, those ions are now becoming part of that electrode, and we're increasing our mass. And what would happen is that we'd actually have the opposite happening to our platinum electron. That hydrogen is actually going to be lost and can revert back into the solution. All right, so just like we did before in our first topic, we have our net reaction. We know that there's two electrons. So those are going to cross out, and we're left with our net reaction. To find our standard cell potential, E naught of the cell, we're going to use our value here for standard cell potential, standard reduction potential of the cell, which is 0.34, and the standard cell potential at the anode, which is 0.00 volts, and we have final value of plus 0.34 volts. What we'll see here is this is how you kind of want to visualize it. Is these are our two half reactions here, and the difference between them is 0.34 volts. Also, too, is that we know that this reaction would be spontaneous because our oxidizing agent is over our reducing agent. As we continue on with this outcome, what we'll find out is what happens if, let's say that we have a non-spontaneous, and our reducing agent is actually over our oxidizing agent, and what we can do with that in a cell. But for now, we're going to focus on this. There's a summary here that I encourage you to read through and then do practice sheet 9. Hopefully that helps explain a little bit. Like I said, go over, watch that video by Tyler DeWitt. I didn't want to film that first part. You can complete your notes, read over them for that first section, but I feel like he does a really good job teaching. That's very clear. And you can see what's going on, where things are being transferred from better than where I can with like pictures on here. All right, hope that helps. Let me know how things are going, and we'll catch up later. Bye.